Hi, so in this video, which covers section 1-1 of the course textbook, I'm just going to introduce dynamics a little bit through some history. So this will be a brief overview of the history of dynamics. You don't necessarily need this to do your homework, but hopefully it'll provide an interesting introduction. I'm just going to kind of cover the highlights as I go through this. I don't want to I don't want to spend a lot of time on it. So early on, scientists and engineers were called philosophers. This goes back quite a ways. And much of their attempt to understand motion was based on planets, the stars, sun and the moon, etc. Um, and so the history will kind of reflect that as I go through some of the early dynamicists, essentially. So Aristotle, in a few hundred years BC, um, kind of wrote about a little bit of everything, but part of it was science and what he called the physics of common sense. He thought that light objects fell more slowly than heavy objects. Turned out not to be true. But at least he was trying to think about things in a systematic way and understand relationships and things like that. Ptolemy came along a few hundred years later. This is now AD. Um, he thought the solar system was geocentric, that is, Earth centered, and everything revolved around the Earth. A logical conclusion until you hear otherwise. It was not till later that people figured out that wasn't the case. Okay, so Kepler believed in a heliocentric system, that is, everything orbiting around the sun, which made a lot more sense. And then he worked out much of the mathematics of orbits and things like that. So he was watching Mars, trying to make observations about how Mars rotated around the sun, and he deduced that the orbit was elliptical, actually, which was pretty impressive given what he had to work with, and that the sun was at the focus of the ellipse. Again, an impressive observation. So he had these three laws. He assumed the orbits were ellipses for all these planets, and the sun was at the focus. Um, he assumed the line, or deduced that a line joining a planet to the sun sweeps out equal areas in equal times as the planet travels around the sun. Let me just give you a quick picture of that. So if this is the sun and this is some planet, it's traveling in this orbit, this elliptical orbit. If you start, for example, at this point and it moves to this point along the arc of the orbit, then it sweeps out this blue area. And if you start from this point, move to this point, it sweeps out this reddish area. And if it takes the same time to go from here to here as from here to here, that is from here to here, then these two areas, the blue one and the reddish one, are the same area. That was his second law. And then the third one was that the ratio of the squares of the periods of two planets is equal to the ratio of the cubes of the semi-major axes, right? So the period is how long it takes to make one revolution. And the semi-major axis is, major is the large diameter, and the semi-major axis is the distance from the center to that furthest point. So it's half the largest diameter. So the square of the ratio of the periods is the same as the cube of the ratio of these semi-major axes. All right, so next was Galileo. Again, strong interest in astronomy. Um, he concluded that a body in its natural state of motion has constant velocity, that the correct law for freely falling bodies is that the distance traveled is proportional to the square of time, and that two bodies of different weight fall at the same rate. So he got that one right. Here we are in around 1600, so it took quite a while to sort that out. Then Newton came along. He wrote three books: the Philosophiae Naturalis, Principia Mathematica, or Principia, and this laid down much of the beginnings of calculus, for example, and a lot of mechanics as well. So He showed that the planets were attracted to the sun by a force which varied as the inverse square of the distance. Again, pretty impressive given what he had for making these observations. And then he presented his three laws of motion. Those are that a particle remains at rest or moves in a straight line with a constant speed as long as the total force acting on the particle is zero. And that sort of leads into F equals ma, right? The time rate of change of momentum of a particle is equal to the force. So if you have a sum of forces, a vector sum of forces on an object, that should equal the mass of the object times its acceleration vector. So if you know the net forces on an object, you can figure out its acceleration and then thereby understand its motion by solving the appropriate equations. And we'll do a lot of that this semester. All right. And then also the forces of action and reaction, and we'll talk about that in a bit. Okay, so the third law is essentially this. If I have two particles, here is Pi, this little green particle, Pj, this little yellow particle. If there's a force acting between them, for example, a gravitational force, then the force on one is equal and opposite to the force on the other. That is Fij, which is the force on particle I due to particle j, is the same magnitude as Fji, which is the force on particle j due to particle I, but in the opposite direction. All right. There's also this second statement, which essentially says those forces are collinear. That's not always true. It depends on the situation. Okay, but the thing to remember is just this equal and opposite concept of the forces. Just as a note, a little bit about Newton's universal law of gravitation. So he worked out that the force between two objects is inversely proportional to the distance. Turns out the force between object 1 and object 2 is the gravitational constant g times the product of the masses of the two objects divided by the square of the distance between them. And then the direction is identified by a unit vector along the line that connects the center of one object to the other. Okay. And for example, with respect to Jupiter, and Neptune, the force on Jupiter from Neptune is g times the mass of Jupiter times the mass of Neptune divided by the square of the distance. And the direction for the force is attractive. So it's along this line between them and attracts the two particles, the two planets to each other. So from this you can actually derive the acceleration due to gravity on the surface of Earth. So the radius of Earth is about 6,400 kilometers. The mass of the Earth is about 6 times 10 to the 24th kilograms. The gravitational constant is here. Okay, so the force between some body of mass m and the Earth is g times that body's mass times the Earth mass divided by the square of the distance. If that body's on the surface of Earth, then it's the radius of the Earth that's the distance between them. So if you work that out, it's 9.8222 times m gives you the force. So if it's mg is what we constantly say, where we use little g for the gravitational, the gravity acceleration due to gravity on Earth, then it's about 9.81 meters per second squared. And it depends a little bit on where you are in the Earth because you're not always the same distance from the center. Earth is not a smooth sphere. Or in British units is 32.2 feet per second squared. All right, so then Euler came along, and what he actually did was made Newton's laws a little more approachable. So he worked out some problems based on Newton's laws, and in fact worked out the principle of linear momentum, and did it in such a way that problems were more easily solved. And in fact, he broke up, for example, F equals ma into its components in our Cartesian coordinate system and said the individual components of the forces are the mass times acceleration in that direction, for example, right? So that's the so-called modern form of Newton's second law, which was done by Euler, right? He also introduced the concept of inertia for the first time, and there was this distinction at that point between inertia and mass, all right? So that's our basic introduction to dynamics. We'll sort of build on what these giants did and use them to solve a variety of dynamics problems as we go through this semester.